Hello students, welcome to this lecture on the static timing analysis, and this is part 2. So in this particular lecture, we will look into the flip-flop designs, and then how do we not violate the whole time failures, or rather, how do we avoid the whole time failures. And also we will start into the latch designs, and then consider the setup time violation and the whole time failures as well for the latch designs. All right, so let's begin. Let's move forward. So meanwhile, I will also get my pointer. Right. So this is from the last lecture, and in the last part of the last lecture, we had seen this particular design of the flops, which is kind of parameterized or characterized with this particular parameters like the T setup time, the T hold time, the TPCQ and TCCQ. So this is something the sequential circuit or the element characterized elements design is given to us with all this set of parameters. And we have an adder, result mux, bypass mux, late bypass mux, which is again going back to the flop design, to the flip-flop design. So we have this set of 4 combinatorial circuit blocks whose characterization in the form of propagation delay and the contamination delays are also given in the form of this this particular values. So one of the questions we had earlier seen was whether this whether this will have any hold time failures. So if I actually calculate the TCDs of this particular 4 blocks of combinatorial circuits, so which I have annotated in the form of stars, it is nothing but 100 picoseconds, 35 picoseconds, 55 picoseconds, and 45 picoseconds. Right. So if I do an addition of this 100 plus 35 plus 55, so it will be 190 plus 45 will be 235 picoseconds. So that will be the contamination delay of all this, the 4 blocks which are in cascaded stages. And then the output of that is going to the flop 2. So what we are expecting is in the the first clock output will give me the this particular input to the adder circuit block, and then the output of this late bypass mux should be captured into the flop design, into the flip-flop design only in the second clock or in the third clock, and it should not get captured within the first clock itself. Right. So so the T hold time, which is kind of characterized for the flop design, is actually 10 picoseconds, and then we also have the TCCQ, the contamination clock to Q, which is around 75 picoseconds. So we to avoid the whole time failures, we know that TCCQ plus TCD of the combinatorial blocks should be greater than the T hold of 10 picoseconds. Then what we can confirm is the output of the late bypass mux will not be captured in the first clock edge of this flip-flop design. Right, so TCCD plus TCCQ turns out to be 235 plus 75, which is around 310 picoseconds, which is naturally greater than the 10 picoseconds. Hence, we say that there is no hold time violation, or there won't be any hold time failures. Right, hope this is clear. So what we really mean is, if I design the clock somewhere here, I'll start designing the clock here. So what we don't want is, the output of this, which is high level of edge of the clock. So this is my clock design. So we don't want everything to be captured here. So this I'll write it as the Q signal. So this one will be the Q1. So what it means is, for the first clock edge, I'll get the Q output, which is nothing but Q1, which will be after the TCCQ, contaminated clock to Q, and then the adder output, result mux output, bypass mux output, late bypass mux output. So I will write it as Q of the the adder, the result mux, the mux, bypass mux, the late bypass mux. So 3 muxes are there. So what we really don't want is with the contamination delay of all this 4 combinatorial blocks, if the output reaches really close to the first clock edge, the output of this, all right, so this will be my combinatorial circuit, which is nothing but adder, muxes, and muxes. So the output of this should not be captured in the first clock edge itself. right? So whatever is the T-hold time, this should, should make sure that this should be ensured that it is away from the T-hold time, so that then only we can clearly say that the contaminated output doesn't get captured in the first clock. It should then easily captured in the second clock edge, right? So that's what we want, and that's why we say that the TCD plus TCCQ should be greater than the T-hold value. Hope this is clear. Moving on. Let's say if the TC, the clock time period, is 885 picoseconds, and this is something which we had seen in the last lecture, where we calculated the propagation delays. From the propagation delays of all these 4 combinatorial blocks, we were able to evaluate what should be the minimum clock time period, and it was around somewhere around 952 picoseconds. But here I'm taking an example where the clock is compromised a bit. So TC is now 885 picoseconds. Now the question is whether there will be any hold time violation, right? So if I look into the TC of 885 picoseconds, what we really want to know is, if I take the propagation delay, that means the output of the adder, output of the result mux, output of the bypass mux, output of the late bypass mux, and these outputs are actually the steady state outputs. Right, when we consider the propagation delay, it is nothing but the steady state outputs. It is not the glitch which is going up and down and then reaching to a steady state value. So this steady state values, we need to know whether it is captured in the first clock or the second clock or the third clock, and then so on. And then I'm going to write it as second clock or third clock, right? And a third clock in the sense second clock edge or the third clock edge, and then try to see whether the same applies for the contaminated output also. If it is not, let's say that if the propagation delay of all these 4 blocks allows the output to be captured only in the third clock edge, but the contaminated output due to this particular values is allowing the flop to capture in the second clock edge, then I think there is a violation. So what we are supposed to do is both design the circuits in such a way that it doesn't not only violate the hold time as well as the setup time failures, but also make sure that it is reaching the proper clock edge for both the propagated delay output and then the contaminated delay output, right? So in that sense, we have to see whether it is kind of the hold time is violated or the setup time is violated, and then proceed further. Right, if we have a TC of 885 picoseconds, so what we are likely to get is this clock having 885 picoseconds. Right, so for the distance or the duration between the first clock edge and then the second clock edge, we have the 885 picoseconds. And let's say that this is the D input. So D input is coming and it is it has arrived earlier than the setup time for the first clock edge, so it is readily available. So the moment it sees the first clock edge, we will get the output of the flop. So this is the output of the flop, and this particular delay is TPCQ, propagation clock to Q. Right. So in this particular diagram, I am considering only about the propagation delays. Right. Now I'm not yet come to the contamination delays, but looking at the setup time failures. Right, so the propagation clock to Q delay, and then after that there will be an adder, output, result mux, bypass mux, late bypass mux. So if I consider the propagation delay of adder, propagation delay of the result mux, propagation delay of the bypass muxes, and the late bypass mux, so which will be nothing but 590 plus 60 plus 70 plus 80. So I will get around 590 plus 60 is 650 plus 150 will be 800 picoseconds. So from here to here, it will be 800 plus 90, so 890 picoseconds. All right, so it comes here at this particular stage, and the clock time period is 885 picoseconds. So here it comes, the output here, which goes to the input to the flop design. So that's why I've written D again here. What it means is the D provided here, after the combinatorial circuit output, it comes back to the flop design with 890 picoseconds. So with respect to the 885 picoseconds of the clock, it is 5 picoseconds late. All right. With respect to the second clock edge, it is 5 picoseconds late. The question is, if it is 5 picoseconds late, whether it is having any setup time failures. The answer is no, the setup time failure will not be there, because we were supposed to arrive somewhere before the second clock edge, right? And if it is not done that, it is also not done, it is also not arriving in between the setup time, right? Setup time in between the setup time means the second clock edge to whatever is the setup time. Let me go back and then say that setup time is 62 picoseconds. So it has also not arrived in between the second clock edge and then the 62 picoseconds. So it has not arrived in between the second clock edge and then the 62 picoseconds. So, right, so in that sense, if I say that this is my 62 picoseconds, it has not arrived in between that, right? So in fact, it has arrived after the second clock edge, right? So there won't be any setup time failure. The only condition is the output generated by the late bypass mux, or the addition of this adder muxes, it is going to be collected by it is going to be captured by the flop at the output side, not in the second clock edge now. It will be captured only in the third clock edge. So somewhere here it is going to get captured. So this will be my third edge. And for the third edge, if I consider the 62 picoseconds of the setup time, it has arrived much earlier than the third clock edge and then the 62 picoseconds of that. Right, so there won't be any setup time failures. Now the question is whether there will be any hold time failures. So I've written here that the hold time is violated, but I've taken the propagation delays and then saying that okay, it is coming in between the 5 picoseconds of the of the hold time. The hold time is only 10 picoseconds, so it is with respect to the second clock edge. So in that sense, it is coming in between the hold time of 10 picoseconds here. So I'll just write it here. It is the 10 picoseconds which is the hold time. So it is arriving in between that, so which is not correct. So there will be an hold time violation. Right? There is another condition here. Right, so if I consider only the contamination delay, right? If I consider only the contamination delay, so let me draw the clock here first. So I'm drawing a very smaller clock this time. Okay, so this is the first edge, this is the second edge. So I'm going to write it as 1, and then this is the second. And I want TCCQ. So let's say that the D signal has arrived much earlier. So this is the first input to the flop number 1, or the flop input. And then the output is getting captured. Let's say that the output is getting captured here just soon after the first clock edge. So this will be my contaminated CCQ, contaminated clock to Q. And then this will be the output of the flop. After that, there will be an adder block. There will be 3 muxes block. So I'm going to say that all of them is a contaminated output. So I'm going to consider this as the contamination TCD, which is nothing but a contaminated delay of all the 4 combinatorial blocks, right? So if I consider this TCCQ and TCD, right, plus TCD. So let me try to find out that particular value, which we had anyways calculated in the earlier slides. So let me go back to the earlier slide number 2, and then say that, okay, this value was 75 picoseconds and 235 picoseconds. So I'm coming back to here. So it is nothing but 75 picoseconds plus 235 picoseconds, which is nothing but 310 picoseconds, right? So with respect to the first clock edge, the output of the last mux, or rather the output of all the 4 combinatorial blocks, is coming after 310 picoseconds. So with respect to the first clock edge, the T-hold is only 10 picoseconds. So it is sufficiently away from the 10 picoseconds. 310 picoseconds is sufficiently away from the 10 picoseconds. But the problem here is, it is now easily available. So the output here, which goes to the input to the flop, it is now easily available and can get captured in the second clock edge. Whereas the propagated, the steady state signal, right, will not be captured here. It is likely to capture after the second clock edge. So that means that it will capture in the third clock edge, right, which is incorrect. So what we have is a propagated output, propagation delay output, to be captured in the third clock edge, but the contaminated output is getting captured in the second clock edge, so which is inconsistent. So what we need to do is add a buffer. So we need to add a buffer, and that's what we are saying here. We need to add a buffer after or in between the 4 combinatorial blocks, so that it surpasses the hold time with respect to the second clock edge. With respect to the second clock edge means the 10 picoseconds after the second clock edge. And if we get this D signal delayed till the 10 picoseconds of the second clock edge, if we can somehow delay that by adding a buffer and then choosing the contamination delay of that particular buffer, so that the output is 10 picoseconds after the second clock edge, we can be rest assured that it will not be captured, the contaminated output will not be captured in the second clock edge, whereas it will go and it will get captured in the third clock edge. And in the third clock edge, anyways, the propagated signal, the steady state output will get captured. So the contaminated output will in fact not be creating any problems, because in the third clock edge, we know that even if it is a contaminated output which is not captured in the first, it is not captured in the second, and whatever is the glitches, it will not be captured in the first and second. Rather, the steady state values will be captured in the third clock edge, right? So in that sense, what should be the buffer, the contamination delay of the buffer? And it is very simple to calculate, because we know that TCCQ and TCD will be there for the contaminated output. So it will be nothing but the clock time period here, TC, which is nothing but 885 picoseconds. So TC minus of this TCCQ plus TCD, and to ensure that after the second clock edge, the 10 picoseconds of the hold time. So I will have T-hold here. That's about it. So my TCD of the buffer should ensure that if I add a block after or in between the 4 combinatorial blocks, it should ensure that the output of that particular, the output which goes as an input to the flop design should arrive only after the T-hold of the second clock edge, so that it will not be captured in the second clock edge, it will be captured only in the third clock edge. Right, so in that sense, it will be nothing but 885 plus T-hold time, which is nothing but 10 picoseconds. So 895 minus of this whole thing will be 310 picoseconds. So it turns out to be, in fact, it should be greater than or equal to that. So it should be greater than or equal to TC, which is 885 plus 10 picoseconds. So 895 picoseconds minus this 310 picoseconds. Right. So in that sense, it will be 85 here and 585 picoseconds. So you can choose 590 picoseconds as, or we can design the buffer such that the TCD, the contamination delay of the buffer, is 590 picoseconds. Right, so that it can easily avoid the second clock edge and it can get captured only in the third clock edge, where the steady state value will be captured. Now the question is, so what should be the propagation delay of that particular buffer which we have used, right? So that the hold time failures is avoided not only in the first clock edge but also in the second clock edge, right? So the TPD of the buffer, so if I look into the previous slide, the TPD of the buffer says that the TPD is 590 plus 60, excuse me, 590 plus 60 is 650, plus 150 is equal to 800 picoseconds. And then this is 90, so 890 picoseconds. And so if I add a buffer somewhere here, right? So this buffer, the maximum delay this buffer can go is make sure that the third clock edge and the output of this buffer should be arriving at least the T setup time for the third clock edge, right? So whenever the third clock edge comes, then the T setup time with respect to the T setup time of the flop design, it should be available, and so that it will be captured in the third clock edge, right? So going back, so this propagation delay of the buffer, should be nothing but the first clock edge to the third clock edge, so that we will have twice the time period of the clock, minus of the 800, which is nothing but the propagation delay of all the combinatorial blocks, TPCQ, that is coming from the propagation of first clock to the Q, output of the flop, and the T setup for the third clock duration. Right, so it should be smaller than 818 picoseconds. T setup is nothing but 62 picoseconds. All right, so this is 62 picoseconds, and TPCQ was nothing but 90 picoseconds. So this was 90 picoseconds. So if I do the calculation, I'll get 818 picoseconds. So that should be the maximum one. So the TPD buffer, we can have it as 817 picoseconds, and TCD could be, so I'm going to write here as TCD of buffer, which we are going to add after the fourth combinatorial circuit, right? Could be nothing but, so this is, 5 and then 8 and 5. So I can choose 586 picoseconds. So we need to design a buffer with its propagation delay as 817 picoseconds and its contamination delay, around 586 picoseconds, so that the contaminated output is avoided in the capturing in the second clock edge, as well as the propagation delay, which is a steady state output, will be captured only in the third clock edge. Right, hope this is clear to everyone, and this is what we are going to follow in our designs to the sequential elements, whether it is a flip-flop designs along with the combinatorial circuit designs, or the latch designs, or the phase latch designs. Right, so let's proceed further to the next kind of the sequential elements, which is called as the latches. And generally, latches are not utilized in terms of how we have utilized the flops. The flops are generally utilized for the clock edges with respect to the clock edges. So we have the combinatorial circuit design element within the two subsequent flop elements, such that the output of the combinatorial circuit 1 will be captured in the second clock edge, and then so on. Right, but in the terms of the latches are actually designed in terms of the levels. It is working or operating in terms of the levels. So if I design a clock here, the latch 1 here is connected to the positive level of the clock. So that means that it will work in the positive level of the clock, and the L3 latches are working again in the positive level of the clock. So all the odd number of latches, L1, L3, L5, those work in the positive level of the clock, whereas the L2, L4 and L6 are all connected to the clock number 2, which is nothing but kind of derived from the clock 1, but it is having it is kind of phase shifted. So the clock 1 and clock 2 are kind of non-overlapping in this particular design or in this particular representation. So the clock 2 is connected such that when the clock 1 is high, the clock 2 is low, and when during some portion of the clock 1, during a low level of the clock 1, the clock 2 will be high. So the latch 2, latch 4, latch 6 and all the even number of latches operates in the high level of the phi 2 clock. So what it really means is it actually operates in the majority portion of the low level of the clock 1. Right, so what we normally use the latches is the one combinatorial circuit will operate in the high level of the clock 1. The second combinatorial circuit operates in the low level, some portion of the low level of the clock 1. And then the third latch will, or the third combinatorial circuit works in the, again, the high level of the clock 1. And then the fourth combinatorial circuit will work only in the some portion of the low level of the clock 1. So in terms of the latches and then with respect to the flip-flop, the difference is because the flip-flops operate only in the clock edges, the combinatorial circuit's output, we make sure that it is captured in the clock edges, in the subsequent clock edges. Whereas here, because of the latch design, we have an ability to have the combinatorial circuit, maybe a faster combinatorial circuit, to be captured in the levels, positive levels as well as the negative levels of the clocks, right? And to do that, what we do is we have the clock 2 representation, which is nothing but coming from the clock 1 and with some time non-overlap, right? And we'll see what is the significance of this time non-overlap in the later slide. So what it really means is the phi 2 is derived from phi 1. So the clock 2 is derived from clock 1. But clock 2 will operate or will be high only during the majority portion of the clock 1 being low. Right. So this is about the discussion about the clocks for this combinatorial circuit designs. Now let's say that this is also called as the transparent phase latches. Right. The reason is it is transparent. It is latches. Latches are nothing but CMOS latches. Works in the transparent mode as well as in the opaque mode, but we are interested in only capturing the output only in the transparent mode. So that's why it is called as the transparent, and then it is a latch design. And it is called as a phase latches. The reason is nothing but if you look into clock 1 and clock 2. Clock 2 is, it's operating only when the clock 1 is low. So it is kind of 180 degrees out of phase, right? So in that sense, it is called as the phase latches. Now let's say that the D1 signal is coming here to the latch 1. And remember that, the latch 1 will operate only during, the latch 1 will operate when the clock 1 is high. So even if the D1 signal comes before the clock or after the clock level, after this particular rising edge, doesn't really matter, because even if it comes after the rising edge, during this entire portion of the clock level being high, it is likely to get captured. And the farthest the D1 signal can come with respect to the clock level high will be nothing but the T setup time before the clock goes to low, right? So the T setup time before the falling edge of this clock, right? Until then we have the high level of the clock, so it should be able to capture it easily. So if the D1 signal is getting high in between this particular clock level high, the Q1, which is nothing but the output of the latch 1, is going to get captured here with the propagation D to Q. So that's why I've written D to Q 1. So 1 represents the latch 1. Now remember that here it is the propagation delay of the D to Q and not the propagation delay of clock to Q, right? So remember in the flip-flop designs, the D used to come before, and it used to be ready before the clock edge going high, and then the output was actually determined whenever the clock does the transition, the rising edge of the transition, right? And that's why the output is with respect to the clock going high to the output. Here it is actually because the clock is already available, whenever the D comes, the output Q1 will be high in this particular case, and that's why we say that it is with respect to the D signal, right, and not with respect to the clock signal, right? So that is the output of the Q1, and then it goes to the combinatorial circuit, which will have some propagation delay, and then it will give the D2 signal. So I'm considering the propagation delay of the combinatorial circuit 1 as TPD1. Notice that this particular title is the maximum delay constraints. So we are considering the maximum delay. We can have it for the combinatorial circuit 1 and 2, right? We can design the combinatorial circuit 1 and 2 such that it will have the maximum delay. So that means that we'll have to consider the propagation delays of the combinatorial circuit. We'll have to consider the propagation delays of the latch designs L1 and L2 and L3. Right, so in this case, so the D2 signal comes after the propagation delay of the first combinatorial circuit. So that is the D2 signal. And after that, the latch 2 is going to get captured. And remember that, the output or rather the D2 signal is arriving, during this phi 2 level being high. So phi 2 level being high, that is when it arrives, and then we'll get the Q2 signal, which is now with respect to the propagation delay of the data D for the latch 2, and then the output of Q, and then the 2 subscript is there so that it represents the latch 2 output, right? So this is the propagation delay of the D input to the Q output for the second latch. right? And then it goes to the combinatorial circuit number 2, goes to the next L3 latch, which is kind of driven by the clock 1, right? So I will have the D3 output, which is which is now coming into the high level of the clock, which is now sufficiently there during the high level of the clock 1, right? And of course in the second clock level, right? This is the first clock level, this is the second clock of the phi 1, right? So if I consider this particular propagated delays, now because of the sufficiently high levels of the clock, right, I can also, if at all I have to design the clock signal here, right? So let's say that the phi 1 clock time period is not given to us, the phi 2 clock time period is not given to us, and if we were to design the clock time period, then what we are likely to do is we'll calculate this TPDQ1, we'll calculate the propagation delay 1 of the combinatorial circuit 1, TPDQ of the latch 2 designs, TPD, which is nothing but a propagation delay of the combinatorial circuit number 2, add them up and say that will be my, anything, those things will be my clock time period. So TC turns out to be, the clock time period turns out to be TPDQ1, TPD1, the TPDQ2 plus TPD2, and anything greater than TC and anything greater than that will be my clock time period. Right? So if at all I were to design, the clock time period, right? So what I will choose is all this 4 components of the propagation delay, and then anything greater than that will be my time period. Right? Now, if we were to, let's say that if we have the clock time period and if we were to design the combinatorial circuit blocks, then what should be the propagation delay of those 2 combinatorial blocks? Right? So looking at this particular equation, we can easily say that the propagation delay of this plus this should ensure that it is less than TC minus TPDQ and TPDQ of both the latches L1 and L2, which is a kind of characterized by the latch design. So we don't have much of a control here. So that's why it is called as a sequencing overhead. So if we were to use the sequential elements to time my outputs of the combinatorial circuit, then there will be an overhead, and in this particular latch design, the overhead comes in the form of TP DQ1 and TP DQ2, right? So that's why it is called as a sequencing overhead, right? Hope this is clear to everyone. So this will be my maximum delay constraints. So the maximum delay constraints for the phase latches, where we want so let me complete this writing, maximum delay constraint. So this is especially for the phase latches, where we want the one part of the combinatorial circuit to work in the high level of the clock, and then the second part of the combinatorial circuits to work in the low level of the clock. And that's why we have used 2 phase clock signals and then 2 phase latches. So one clock given to the latch number 1, latch number 3, latch number 5, and all the odd latches. And then the 180-degree phase shifted clock is provided to the latch number 2, latch number 4, latch number 6, and so on, all the even number of latches. Right? If suppose that we have to design the combinatorial circuits, then the maximum delay, if at all the time period is given, then it should be like this, TC minus of TPDQ1 plus TPDQ2. Right? And the T non-overlap time doesn't come into the picture of this particular expression at all, right? So the T non-overlap, although it is there, it doesn't come because we have the TPD1, which is, it is designed in such a way that it comes during the clock level being high. So the TPDs are designed to in a way that the output of the combinatorial circuits are coming during the clock levels being high. So in this case, the clock level being high, and in this case, the clock level being high, right?